Before we go any further with transactions, let's just take a step back and re-examine the problem we're trying to solve. So we have concurrent clients connected to the same web server in the same database, and those clients might be doing things at the same time that conflict with each other, so there's a race condition that we're trying to prevent. So a more straightforward way to prevent a race condition might just be this. Why don't we just use a software lock in C#? So a mutex. We can just put a lock around the controller that does the select and the if and the insert, or just around the whole critical section. So why don't we do that? It would look something like this in C#. So here's our checkout book controller from before. And instead of doing all this stuff with the transaction to try to prevent the race condition, why don't we just do lock, some object, and this is just pseudocodes. X doesn't actually exist, but we lock some object and then put a big scope around the select part, the if statement part, and all the way up, including the save changes. So now this entire critical section is protected by a mutex, and the problem is solved in theory. Well, let's see. So here is a more accurate picture of how web servers work. It's not just one machine and one process running somewhere. There are many machines, and not necessarily even on the same network. These machines, one of them might be on the West Coast, one of them might be on the East Coast, or on a different continent or something. And so if we tried to do this where each web server is running the same code and each web server is locking the critical section, that's going to prevent races between these two clients, but it is not going to prevent races between these two clients because these locks here are on completely separate machines, and they only provide mutual exclusion between threads on that same machine. So there is no mutual exclusion between the two different servers. So what we need to do is we need to push the locking mechanism to the common point, or in other words, to the database. So we need something like this, where the database is locked, and then we do our selects and our inserts or whatever, and then we unlock it. But notice this is not start transaction and commit, because that's not what transactions do. They are not locks. And this is kind of just pseudocode, pseudo SQL. We need something like a lock and unlock. And transactions will sort of provide a way to do that. We will be able to solve the problem with them, but again, a transaction is still not a mutex. So how can we make a transaction look more like this? Well, it comes down to the isolation part in ACID. So isolation means operations must not interfere with each other, and transactions therefore need to provide some form of synchronization to detect conflicts, and we saw that in the last video. What the transaction decided was a conflict was when trying to say write the same row to the same table, but trying to read information out of the same table was not a conflict. We were able to do that at the same time in two different transactions. But that was the default behavior, and as I mentioned, we can change the isolation level. So an isolation level in SQL is just a way of controlling how much synchronization there is between transactions, and there are 4 of them in SQL. Read uncommitted, read committed, repeatable read, and serializable. And these are in order of the least isolated to the most isolated. And when you would want to use these depends on what you're doing, but in general, the less isolated it is, the faster it is, because there's going to be less synchronization required, and the more isolated, the slower. So sometimes if you can prove that there will never be any conflicts, then you might as well use read uncommitted, since it'll just be faster. But sometimes we need all the way up to serializable. And in the last video, we were experimenting with the default behavior, and that is repeatable read. So that's what we were seeing, is how repeatable read works. And we'll go into detail about what each of these things mean. Their names basically mean what phenomena do they allow? So read uncommitted will allow for a transaction to read uncommitted data from another transaction. So let's look at each of these. Read uncommitted means basically that a transaction can read non-existent data, or data that is only temporary and has not been committed yet. So if we have two sessions here, they both start a transaction at the same time. One of them does an insert, and then the other one just does a select star. It will see the value that was inserted by the other transaction. And I have rollback here. I specifically am rolling back instead of committing to make the point that this one that session 2 saw was never actually a real one. It was never real data. So read uncommitted lets us read non-existent data. If we were to do another read down here, we would not see the 1. Read committed, as the name implies, just means that a transaction can read committed data, but it will not read uncommitted data from another transaction. So I have a sort of a similar setup, 2 sessions, both starting a transaction at the same time. If session 1 does an insert and then session 2 does a select, it will still not see anything from the other session because it hasn't been committed yet. So as soon as session 1 commits, now session 2 can see the 1 row, even though session 2 is still within a transaction. So in these diagrams I'm showing time is always going down on the downward axis. So this insert happens before this select, and it still sees 0 rows, but then the commit happens before the second select, so that's why it sees 1 row. So this phenomenon right here of a single transaction performing the exact same select twice in a row without any modifications in between, this is called a non-repeatable read. And this is usually an undesirable phenomenon. You don't want the data just changing mysteriously from within a transaction. If you were not in a transaction, you might expect the data to change from other sessions. But we may want to prevent this from ever happening. And if we ever select something, then we would want that data to be persistent and know that it's always going to have that state unless this transaction changes it. So if you want to prevent this phenomenon from happening, then you can use the isolation level called repeatable read. And that does exactly what it sounds like it does. Any read within a transaction will always be repeatable. You can think of the way this works as each transaction gets its own sandbox where the outside world can't interfere with it. That's not actually how it works, but we can think of it that way. So once a transaction has looked at something or selected something, then no other transaction will be able to change what it sees about that thing that it has selected. So I have the same setup here, 2 sessions starting a transaction at the same time. Session 2 does its select first, so it gets a snapshot of X and it sees 0 rows. And then it will always see 0 rows if it does that same select again, regardless of what the outside world is doing. So it's a repeatable read. So even though we have this commit right here from the other transaction, where it has inserted something into that table, session 2 does not see it. It has to be a repeatable read. And then it does see it, though, after we've committed. Now, if it does the same select, it will see 1 row. So these 2 reads are repeatable because they are within the transaction. This third read is not repeatable because it's after the commit. And finally, the serializable isolation level. This one means that transactions at this level must behave as though they were serialized with respect to each other. Or in other words, one of them runs and then the other one runs, not in parallel. We don't actually need to remove parallelism all the time, but the outcome of a serializable transaction must be as though it was the only one running at that isolation level at that time. The implications of this are that a select in one serializable transaction can stall an insert in another, and vice versa. So let's look at how that works. Same setup with 2 sessions, 2 transactions. If session 1 does an insert into some table, it has now essentially blocked other serializable transactions from being able to do anything with those rows, including select from them. So if session 2 now goes and tries to select from X, even at a later time, the system delays the select. So it doesn't just return some old value or something, it actually just pauses that session. And that's because session 2 doesn't know what should be selected yet. It depends on whether session 1 is committed or rolled back. If it's committed, it gets the 1 row returned. If it's rolled back, then it should see 0 rows. Now let's look at kind of just reordering the sequence of these operations though. Exact same operations, but what if session 2 gets to go first, and so it does its select first. Now when session 1 tries to do its insert, the insert is actually stalled. So an insert can be stalled by a select with serializable transactions. Essentially, you can think of this as when session 2 does this select, it is claiming those rows for its own sole use. So nobody else can insert or modify those rows. No other serializable transaction. And well, why does that matter? Like, why, if session 2 is just selecting, why can't session 1 insert after the fact? Well, because it doesn't know what session 2 might be doing later. So what if session 2 then goes and does an insert into X? What we want out of a serializable transaction is any time in between a select and an insert, we have to be able to assume that nothing has changed, regardless of what other transactions are doing, even if they've committed already. So that's why session 1 has to be delayed. It cannot be allowed to commit yet because session 2 needs to know that nothing has changed. So in this case, if session 2 is doing an insert of X into X of value 1, we actually end up with a conflict because session 1 was trying to insert a 1, so we get a primary key violation. So as soon as session 2 commits, session 1 will fail. The transaction will fail, and it will be rolled back. So as I already briefly mentioned, one of the goals of Serializable is that once we select something, we want to be assured that we have sole ownership of that, and nobody else will be changing it until we're done with this transaction. We can still change it, and that's kind of the point, is that we've selected something and we might make some decisions based on what we selected and then change something. Kind of like our example where we selected the number of books left available and then made a decision whether to insert or not based on that answer. We need for those operations to be atomic in order for that to work. Now you might be wondering, what is the difference between this and repeatable read? It kind of looks like repeatable read would give us this property as well. Let's go back to repeatable read. And so it has that property where once I select something, if I select it again, it returns the same number of rows, but that is an illusion. It only appears to return the same number of rows. Repeatable read will let some other transaction do this commit and change the actual database after selecting something that I want to be unchanged. So if we do want that to truly be unchanged, then we can't use repeatable read, we have to use serializable. Serializable will actually block this insert after this select has been made. And that is the key difference, and that is what gives us this behavior here. And this behavior here is going to help us fix the problem in the library database where we had a race condition in which it was allowing the last book to be checked out by concurrent customers.